Hello there, Mr. Sutton here, bringing you the BC Calculus 7.5 Extra Practice Number 1 solutions on alternating series error bound. So plug it in the calculator, we end up with an answer of 0.0101. Now if you need to round this to the nearest 3 decimals, then we're going to round up on that third decimal automatically so that we have an answer, our error is less than whatever this number is. So I'm going to write less than 0.011. And that is going to be an up or down bound now to 3 decimals on our error. For this no calculator free response, we have a power series defined as follows here. And then we want to find f prime of 0, f double prime of 0, and do some stuff afterwards. Well, f prime of 0, that's going to be the coefficient of x to the first power in this series. Since there is no x to the first power in the series, that means f prime of 0 must be 0 itself. For f double prime of 0, we're going to look at the coefficient of one of our terms here. In general, the x squared coefficient is f double prime over 2 factorial. Well, the coefficient of x squared in this particular series is negative 1 over 3 factorial. So if f double prime of 0 over 2 factorial equals this, we can solve for f double prime of 0 by multiplying both sides by 2 factorial. So that's going to be negative 2 factorial over 3 factorial. Well, this is really just 2 over 6, which reduces to negative 1/3. So there's our f double prime of 0, which we didn't actually have to reduce. Now the next part of the question, they want us to figure out if f has a local min, max, or neither at 0. So the key on this one is realizing that your first derivative of f is 0, so we have a critical value, and the second derivative is a negative number. Once you've shown that this is negative and that the first derivative was 0, since we're concave down, we can conclude that the function has a local max at x equals 0 by the second derivative test. For this part of the problem, they want us to show that 1 minus 1 over 3 factorial approximates f of 1 with error less than 1/100th. So we notice that we have an alternating series here, minus, plus, and that's going to definitely be the case. If you have an x value of 1, it's going to alternate. We also notice, since your denominator is growing, while if you're plugging in 1, your numerator is actually staying the same, this is also going to be a decreasing series down to 0. So since our terms alternate and decrease in absolute value to 0, that tells us we can use the alternating series error bound, which says that our error is going to be less than the absolute value of the next term. Well, what's the next term? If the first two terms were 1 and minus 1 over 3 factorial, our next term is going to be 1 to the 4th over 5 factorial. So the error is going to be less than the absolute value of that, which is to say 1 over 120 if you multiply out that factorial. Now 1 over 120, and this is the important part of all this, is less than 1 over 100. It has a larger denominator. So therefore, our error is less than 1 over 100, and we have proven what they told us to set out and prove. For this problem, they want us to show that y equals f of x, which they gave us up here, is the solution to the differential equation xy prime plus y equals cosine of x. So if you try to do this as a standard Diffie-Q problem by separating variables and whatnot, it's not going to work out very well, especially because you're supposed to end up with some crazy series. So we're going to kind of go backwards on this problem. We're going to take this series and try to transform it into this differential equation, and hopefully the left side and the right side match up. So to do this, let's start with y prime, because we already know what y is. So let's get y prime. Y prime, that's going to be the derivative of all this. So that's going to be, let's see here, going from left to right, derivative of 1 is 0. Derivative of negative x squared over 3 factorial, that's going to be 2 over 3 factorial times x, and we'll have a negative for that, so 2x over 3 factorial. Next we've got plus, let's see, 4x cubed over 5 factorial, and then minus 6x to the 5th over 7 factorial, and so on and so forth, and we'll do the general term just to be on the safe side. So this is going to be negative 1 to the n times 2n times x to the 2n minus 1 over 2n plus 1 factorial. Next step, we have to multiply all of this by x to get this xy prime term. So doing that, now we have negative 2x squared over 3 factorial, 4x to the 4th, 6x to the 6th over 7 factorial, and over here we now have negative 1 to the n times 2n times x to the 2n, because we added 1 to the exponent. And our last thing we need to do to get the left side of this equation is simply just add y. Okay, well, if I'm adding y, I'm adding all this stuff again. So going from left to right and combining like terms until we get sick of doing it, we've got 1 plus, well, there's no 1 over here, so 1. And then we've got, let's see here, we have an x squared, we have an x squared, we can combine those. So this is going to be negative 1x squared over 3 factorial minus 2x squared over 3 factorial. Now we're in luck because we have a common denominator of 3 factorial. So this adds up to negative 3x squared over 3 factorial. Next, 1x to x to the 4th over 5 factorial with 4x to the 4th adds up to 5x to the 4th over 5 factorial. And as luck would have it, this negative 1x to the 6th combines with this negative 6x to the 6th to give us negative 7x to the 6th over 7 factorial. And this is going to keep on happening all the way to our general term, where we're going to get 2n plus 1 x to the 2n and all the rest of this stuff. Okay, this doesn't really look like much of anything just yet, so let's simplify it a little bit, because at this point you either need to incorporate cosine or you need to show that all of this stuff is equivalent to cosine. So let's go ahead now and simplify. So these 3's here can simplify, except this is 3 versus 3 factorial. So that's going to just get rid of the head of the factorial chain here and leave us with a 2 downstairs. So we're going to have a 1, that stays the same, and now we were subtracting x squared over 2 factorial, plus this is going to be x to the 4th over 4 factorial, just the 5's cancel, minus x to the 6th over 6 factorial, and this keeps happening all the way over here until we get negative 1 to the n. 2n plus 1 cancels with the head of this chain. You're left with a 2n factorial downstairs, and x to the 2n in the numerator. Now, all of this, if you look closely, this is actually your pre-memorized series for cosine. So really, there's nowhere else to go at this point other than saying that this equals cosine, because this is one they expect you to know. On this no calculator problem, we have a function with all derivatives of all orders for some real numbers x, and we have a portion of the graph of f. That's great. We also have a tangent line and some other selected derivatives at orders of 2, 3, and 4 given in a table. Our first task, based on all this, we want to write the third degree Taylor polynomial for f about x equals 0. So using my general Taylor formula, I'm going to have to build this one from scratch. I need the function value and the first 3 derivatives at x equals 0. So f of 0, we actually are given that in the table. That's the y value of this parabola looking kind of thing on the y-axis. So that's just going to be 3 right there. F prime of 0, that's going to be the slope of the tangent line at x equals 0. So that's going to be, let's see, we're going down 2 over 1, so that's a slope of negative 2 for f prime of 0. For f double prime of 0, well, now we look at this table here. That's going to be 3. They just flat out gave it to us. And f triple prime of 0, also in the table, that's negative 23 over 2. Setting up my general Taylor formula here, I'm going to have f of 0, which is 3. So this is p sub 3, third degree polynomial. And then we also have f prime of 0 times x, so this will be negative 2x. Then f double prime of 0 over 2 factorial, so 3 over 2 factorial being added, and x squared. And then finally we have f triple prime of 0 over 3 factorial x cubed. So this is going to be negative 23 over, and this is going to be 2 times 3 factorial down there with an x cubed. And if we really wanted to simplify this, well, this is really just 3 over 2, and this last one is 23 over, let's see, this is going to be 12 x cubed then. For this part of the problem, they want the first 3 non-zero terms of a Maclaurin series for e to the x. then the second degree Taylor polynomial for e to the x f of x about x equals 0. Well, we would have needed to figure out e to the x anyway to get this other piece. So it's nice that they're actually going to make this part of our credit for the problem. So e to the x, this is one where you hopefully have it memorized. If not, it's pretty quick to derive it. But we've got 1 is always the way this series starts, plus x, plus this will be x squared over 2 factorial, and they didn't want more than that. So that was a pretty easy point, just writing out the first 3 terms of series that we already should have memorized. All right, now f of x, recall from part A, we figured out was this expression here. And there was more to it, but I'm only writing out the first 3 terms because the next part of the problem here, they want a second degree Taylor polynomial for e to the x times f of x. So I'm not going to need anything higher than second power in either of these because I'm multiplying these 2 series together. And this is where this problem gets a little bit tougher because you're multiplying 2 infinite series together. So how do we do this? Well, we basically have a giant distribution problem going on here. So we have every term in the E series getting multiplied by every term in the F series. So I've got 1 times f of x essentially, plus x times f of x, and we can split up the problem like this, and then plus x squared over 2 times f of x, and nothing else is going to give me anything with a degree, or nothing else is going to give me with a degree 2 or lower, so I'm just going to stop here with x squared over 2 times f of x. Now I'm not actually going to multiply 1 times the entire f series, I'm just going to show part of that. So I've got 1 times 3, which is 3, that was tough, and then we have negative 2x plus 3 halves x squared, so just multiplying by everything that is going to give me second power or lower in the f series. Next, I'm going to skip a bunch of terms, and now I'll start multiplying x times my f series. So we have x times 3, 3x, x times negative 2x, that's negative 2x squared, and I've hit the second power, so x times everything else is going to give me something higher than x squared, so I'm not going to bother doing it. Last but not least, we have x squared over 2 times 3, that's 3 halves x squared, and everything else now I multiply this x squared by in the f series is going to give me something higher than second power, so I'm going to stop there with that one as well. Okay, well, at this point we need to collect like terms because they just wanted the second degree Taylor polynomial. So you don't have to have coefficients that are simplified, but you do need to have all the like terms together. So starting on the left, we just have 3. That's the lonely constant. And then let's see here. We've also got negative 2x plus 3x, and there's no other x term, so that's going to be plus x. And notice at the back here that I wrote approximately equals because I'm not writing out the entire series anymore. I'm just writing out the first 3 terms. So this is definitely an approximation of everything we did back up here. Okay, so my last thing now, I have the quadratic terms I have to add together. So let's do these fractions first. 3 halves plus 3 halves, well that's really 6 halves or just 3, so that's 3x squared. But we also have a minus 2x squared here, so that all adds up to just plus x squared. And there we are. On this next part of the problem, they're defining h as the integral from 0 to x of f of t dt. They want us to use our polynomial that we made in part A, which was this expression here, to find an approximation for h of 1. Well, h of 1 is just going to be the integral from 0 to 1 of, well, it's approximately going to be equal to the integral from 0 to 1 of our p3 that we just did here, p sub 3 of t dt. So let me go ahead and actually take the antiderivative and plug in 0 and 1. So we've got 3t minus, this is going to be, let's see, this is normally 2t, bumps up to a 2, so we've got minus t squared. And this will become, if this bumps up to a 3, this will be 1 half t cubed. And then this last one, this bumps up to a 4, dividing, we've got, let's see, minus 23 over 48 x to the 4th. And that'll be t to the 4th actually. Evaluate that from 0 to 1. We've got all this stuff with 1 plugged in, minus all this stuff with 0 plugged in, but all this stuff with 0 plugged in has a value of 0, so I'm not going to bother writing that. I could actually stop here and be done with it, or I could simplify. So 3 minus 1 is 2. We're adding 1/2. So that's going to be, let's see, 5 halves minus 23 48ths. Well, how many 48ths is that? This is a calculator problem, so if I really want to do this, I'm going to do it on the calculator. Although, come to think of it, I mean, it's not horrible. 5 halves, I have to multiply that by 24 over 24 to get 48ths. So 5 times 24, that's going to be 120. So 120 minus 23, that's 97 over 48, which we can't really reduce anymore, so we're just going to stop here. Really should have stopped like 10 seconds ago. On this last part, it's known the Maclaurin series for h converges to h of x for all real numbers, also known the individual terms of the series for h of 1, alternate in sign and decrease in absolute value to 0. Okay, well, they're essentially telling us we can use the alternating series error bound here, and here it comes. Use the alternating series error bound to show that the approximation from part C differs from h of 1 by at most 0.45. Okay, so our terms alternate and decrease in absolute value to 0. That means, by the alternating series error bound, that the error on this thing, which 0.45 is kind of our suggested error, that's going to be less than the absolute value of the next term of the h series. Well, to get the next term of the h series, we're going to need the next term of the f series. We already had the first 3 terms, but to get the next term, that's going to be f quadruple prime, the 4th derivative of f at 0, divided by 4 factorial with an x to the 4th next to it. So that's going to be 54 from our table, 54 over 4 factorial x to the 4th. And now actually plugging this in the integral to get the next term of h, the antiderivative of this now, from 0 to x, this is going to be, let's say if we just bump that up by 1 exponent, this is x to the 5th over, and then we've got 5 times 4 factorial, which is really 5 factorial. Still got 54 on top. So this is the algebraic expression for the next term, but now we actually have to plug in 1 to figure out the value of the next term, because our error is going to be less than the absolute value of that. So 54 over 5 factorial, what is it? Well, let's go to the calculator for this. If we do 54 divided by 5 factorial, and by the way, we have an invisible 1 to the 5th that we're not bothering to write, this comes out to 0.45, which is exactly the error bound they wanted us to show.